writing and evaluating a function modeling continuous exponential growth, or decay, given doubling time or half-life. So if it's a decay problem, it'll very likely mention half-life. If it's an exponential growth problem, it'll probably say doubling time or tripling time, right? Things would have to grow and get bigger. A specific radioactive substance follows a continuous exponential decay model. It has a half-life of 18 hours. At the start of the experiment, 33.3 grams is present. How much will be present in 14 hours? Do not round any intermediate computations and round your answer to the nearest tenth. The first thing you want to do is get a little bit of a picture in your head that this is actually a decay model. So we're going to focus in the first quadrant. So this is quadrant 1 up here. And we do know the y-intercept. It says at the start of the experiment, 33.3 grams is present. I'm going to call the grams axis to be y of t. So y of t represents grams. I'm going to start labeling things. And t is your independent variable, so we have your t-axis, and t is actually in hours. So when t is 0, we know that it's at 33.3 grams. So the y-intercept is 33.3, and we have a decay model. So it was actually very, very steep and very, very up high in quadrant 2, but then it's actually going to decay and probably get less and less over time. So how do we write this? Well, you do want to memorize such a model. In this case, y of t is being expressed as some initial population, I call it p sub naught, times base e, and it's a decay, so we got to have a negative r times t, where r is greater than 0, and you can see that t is greater than or equal to 0. And that's where we're going to start. We're going to start with that y of t model. Y of t model is a continuous exponential decay, where p sub naught is e to the negative rt, r is greater than 0, and we're given p sub naught in the problem. Remember that p sub naught is simply p of 0, and that is actually given. P of 0 is 33.3. You're also given that the half-life is 18 hours. We're going to use that first. That piece of information came first in the story problem, and we're actually going to go ahead and use this information first. How do we interpret this half-life of 18 hours into our y of t model? Well, we're going to see that y of 18, well, I'll write it over here. Y of 18 is equal to 1/2 times p naught. And we know that p naught is not 0. I'm going to take this and substitute it over here. I'm going to substitute it into this equation. So we're going to write y of p naught when t is 18. So 1/2 p naught is y of t when t is 18. So that goes on the left-hand side. We're substituting right now. Is now equal to p naught e to the negative r, and t is 18. Now we could solve for r. Divide the entire sides by p naught. And how come we could divide by a variable? You were always taught never divide by a variable unless you know why. And that is because p naught is not 0. You can see it right here. 33.3 is not 0. Now we have 1/2 is equal to e to the negative 18 times r. Take the natural log of both sides. We'll use the inverse function of the exponential function to help us find r. Now we have negative 18r is equal to ln of 1/2. Divide the entire sides by negative 18 because negative 18 is not 0. And keep in mind that ln of 1/2 is a negative number. So a negative number divided by a negative number is indeed positive. So this r does make sense. What do we have now? Well, we have r, which allows us to write our model. A lot of times mathematics is about finding a model or approximating a model. Our model, remember, is y of t, which is in grams, is now equal to p naught e to the negative rt, but we're going to substitute our constants. P naught is actually 33.3, e is base e, which is just a number, and then negative r. What's r? It's ln of 1/2 over what? Negative 18 times t. Now you know that a negative times a negative is a positive, so I am going to erase these two negative signs. And so we get our model. And this is really one of the key steps in the problem. I'm actually going to circle that. That's how important it is. The first thing you want to do is use the half-life. The second thing you want to do is get your model. Now the third thing is go back and read the problem again and answer the question. How much will be present in 14 hours? And this is where function notation is so amazing. This is where, if you understand function notation, you'll start to understand English and mathematics and English. So just got to remember 14 is actually described in hours. So that is a t value. All we have to do now is substitute that 14 into our function. We will simply write y of 14 and evaluate this expression. 33.3 e to the ln of 1/2 over 18 times it by 14. This is now equal to 33.3 ln, oh, not ln, I misread there, base e, 14 over 18, that's just 7/9. 7/9 times ln of 1/2. And we gotta expect this number to be what? Less than 33.3 grams. Take your handy dandy calculator and be able to compute this. So look for base e on your calculator. Then we want I get this number here. I get this new expression to be 19,42270,851 ... That's a decimal that keeps going on forever and forever and forever. The instructions say to round your answer to the nearest tenth. So if it says round your answer to the nearest tenth, we simply look at the hundredths place. Hundredths place is 2, so we are going to round this down to 19.4. 19.4 what? Centuries? Seconds? Milliseconds? Make sure you always write your units on your paper. And if the problem is given to you in words and sentences, you probably should respond back in a sentence. What are we answering here? Oh, this is exactly why you go back and try to answer the problem in a complete sentence. What mistake did I make, guys? Correct me here. How much will be present in 14 hours? That can't be right. I can't say we have 19.4 hours in 14 hours. That's a whole lot of nonsense. So make sure you correct these units. That cannot be right. Another reason why you want to write it back using words and a complete sentence. This has to be grams. So a little bit past 18 hours, we should get oh, sorry. Well, we're not past 18 hours. It's not quite 18 hours yet. So we should not reach half of 33.3 yet. And that is exactly what has happened. We haven't reached half of 33.3 yet. Half of 33.3 would be around 16 or 17. Somewhere between 16 and 17, and we only have 19.4. So the computation you made makes complete sense, and we're very, very confident that this is the right answer. Now I need to write a sentence here. Let's write a one-sentence summary. How much will be present in 14 hours? About 19.4 grams of this radioactive substance. Is present in 14 hours. It's a good thing that you try to write this in a complete sentence. That way you catch your own mistakes. I want to circle this. Even though you're circling the final answer, make sure you show all your work, show it in a nice organized manner. You don't have to imagine the graph. It's just good intuition if you have the graph in your head already. You've been graphing a lot, so take advantage of those graphs that you've been graphing a lot over and over and over again.